On June 27, 2023, NASA announced that one of its Mars rovers had detected an anomaly in its wheel bearings, preventing it from carrying out its primary science mission. Within 2 days, engineers had diagnosed the problem as a small rock stuck in the bearing S lubricant and fixed it with a sequence of maneuvers, including driving over the rock. This is impressive, but it's less impressive than it would have been if the rover had fixed itself. And as part of their recent astrobiology strategy, NASA has committed to landing autonomous rovers on Mars by the end of the decade. I'm going to explain how autonomy can help us answer fundamental questions about our universe, why we're integrating AI into our spacecraft now more than ever before, what sort of missions this technology will enable, and the unique challenges we face when programming machines to survive in the harshest environments known to humankind. If you like optimistic science and tech stories, consider subscribing for more deep dives like this one. As part of our new series exploring artificial intelligence, today we'll be looking at the first 6 missions slated to put AI to work in outer space. So, let's get started. Okay, title card with glitch logo sting. Now, we could start this list with the 24 satellites launched last year by SpaceX's Starlink division, which are currently testing a communications network in low Earth orbit. Or we could look at the sleek little robots hopping around the moon right now, collecting samples for return to Earth or chasing each other through the asteroid belt. But these pale in comparison to the projects we're going to see over the next few years. Chapter 1. The International Space Station has long been a testing ground for autonomy, allowing researchers to study how humans and machines work together in microgravity. But on July 2023, Russia undocked the last of its modules, leaving the ISS without any Russian cosmonauts on board for the first time in more than 20 years. Soon after, the United States will attempt to dock a commercial vehicle to the orbiting lab using a vision-based autonomous docking system developed by the company Nanoracks. This system has already been tested extensively on CubeSats, but it will need to perform flawlessly to successfully attach to the ISS and deploy payloads such as the Private Space Telescope. Polaris is being built by the company named Origin Space Systems. Founded by former NASA astronaut Tom Weiss, it will conduct experiments in astrophysics, biology, and materials science, as well as test technologies required for future crewed missions to the Moon and Mars. But while low Earth orbit might seem like the perfect place to start testing autonomy, in my opinion, the real action begins beyond the atmosphere. Chapter 2. In 2025, NASA plans to launch the Dragonfly spacecraft on a mission to Titan, Saturn's largest moon. Scientists believe Titan is one of only a handful of places in the solar system that could support life as we do and know it. And Dragonfly will land on the moon's surface, collect samples and even drill below the surface to search for organic molecules and chemical evidence of past or present life. Most excitingly, though, Dragonfly will be the first autonomous lander to operate on an extraterrestrial body outside the Earth's moon. NASA believes Titan's dense atmosphere makes landing a vehicle there significantly harder than landing on Mars, so the craft will spend several months descending through the atmosphere before finally touching down. During descent, the craft will dodge obstacles using its onboard computer vision algorithms and land in a location not chosen from the safety of Earth, but based on what it sees in real time. It's important to note here that autonomy doesn't mean fully autonomous. There will be a ground station keeping tabs on Dragonfly and giving high-level commands. But it does mean that Once Dragonfly leaves Earth's gravitational pull, human intervention will be too slow to be useful. So every decision made during landing, sampling, and scientific investigation will be made autonomously by the spacecraft. Dragonfly isn't just designed to discover new things about the universe. It's also a testbed for future missions to similarly complex destinations. Chapter 3. Take, for instance, Europa Clipper. A mission to Jupiter's ocean moon set to launch in October of 2024, like Titan. Europa Clipper will spend months cruising through the solar system before beginning its descent into orbit around the moon. Once there, it will begin performing close flybys to scout out locations for a future lander. But unlike Dragonfly, Europa Clipper will not attempt to land itself. Instead, the main challenge for this mission will be navigating Jupiter's intense radiation belts, which are hundreds of times stronger than those surrounding Earth. NASA expects these radiation levels to damage Clipper's electronics, corrupt its data, and eventually cause components to fail. To deal with this, Clipper will be equipped with a suite of tools to detect and correct errors in its systems as they happen. And like Dragonfly, it will carry cameras for navigation. Except instead of dodging rocks, Clipper will use its cameras to identify safe paths through Jupiter's radiation belts. Europa Clipper is another step towards answering the question, how far can we push autonomy? But it also marks a turning point in the economics of space exploration. Chapter 4. Last year, NASA reported that they had achieved a major milestone in their goal to make launching payloads to orbit 10 times cheaper. Their target price is $2 million per launch. And given the sheer number of companies vying for contracts to take satellite payloads to space, competition must be working. But even with all these advances, there are still costs associated with getting your payload into space, whether that's getting a satellite into orbit or a rover onto the surface of Mars. And that's where the final 3 missions on this list come in. They're not just pushing the limits of autonomy. They're pushing the boundaries of what it means to explore space. The first of these is the Psyche mission, set to launch in October 2023. Its destination is the metal-rich asteroid of the same name, which scientists expect to find orbiting the sun between Mars and Jupiter. Its primary scientific objective is to determine whether Psyche is the exposed core of a planet-sized object that lost its outer layers due to a catastrophic collision. But the mission will also test a new navigation system called the Autonomous Positioning System, enabling operations in regolith or apex, using a combination of computer, vision, and machine learning. Apex will allow Psyche to navigate and map its environment without relying on signals from Earth, because Psyche won't have a traditional lander. All of its instruments will be mounted directly onto the spacecraft, which will hover over the asteroid's surface while it conducts experiments. After Psyche, we'll learn whether a machine can navigate unknown terrain and map it in real time. Chapter 5. But some missions won't require autonomous navigation or sample collection. They'll require robots capable of repairing themselves. DARPAS Robotics Manufacturing and Autonomy Program, otherwise known as Project RMA, aims to develop robots that can manufacture parts from raw materials. One application of this technology could be a machine that uses the resources found on an asteroid to build and repair itself. While the concept of in-space manufacturing is not new, most previous concepts relied on bringing a 3D printer along with the materials necessary to make any parts the robot might need. Project RMA changes things by proposing robots that mine raw materials from asteroids and construct parts from them. These robots would not only be able to repair themselves, but also build infrastructure for larger-scale operations in deep space. And speaking of infrastructure, the final project I want to talk about is the Lunar Gateway Space Station, scheduled to begin operations in 2024. This station is the linchpin of NASA's new Artemis program, which aims to establish a permanent human presence on the Moon once operational. The station will serve as a staging ground for missions to the lunar surface, housing both crew and cargo before they descend to the Moon. Gateway will also serve as a platform for scientific research, allowing scientists to study the Moon in greater detail than ever before. But perhaps most excitingly, the station will feature an autonomous airlock. Cargo vehicles will enter through one door and crew vehicles through another. Then the airlock will depressurize, allowing either a rover, a lander, or a human crew to exit directly onto the surface of the Moon. The biggest advantage of having an autonomous airlock is that it can operate whenever it has enough power, regardless of whether or not there's a human crew member available to operate it. This means missions to the lunar surface can be planned and executed much faster. So that was a quick tour of 6 missions taking autonomy to new heights. But it's not quite the whole story. Chapter 6. Let's take a moment to dispel some myths and clarify some facts about autonomy. First of all, machines can't replace scientists. Machines can collect samples and run experiments autonomously, but they still need scientists to design the experiment and analyze the results. Autonomy can help speed up scientific progress by allowing robots to do the dirty work, but it won't replace the human element. Secondly, autonomy isn't always better. Sometimes it's easier and more efficient to control a process manually, especially if the machine encounters something it wasn't programmed for. For example, the Curiosity rover landed on Mars in August 2012 and began transmitting back images almost immediately. But the first image it sent back was corrupted, so the team couldn't see any of the landing data until they reset the camera. This is a relatively simple example, but it shows that even small problems can slow down a mission if the machine tries to solve them on its own. In most cases, it's much more efficient to have a team of experts on the ground who can quickly diagnose and fix any problems that come up. Finally, autonomy doesn't always mean safety. We often hear about AI making decisions faster than humans or operating machines more safely than humans. But this isn't always true. In fact, many autonomous systems are designed to operate in ways that humans couldn't, such as in environments with extremely high levels of radiation or on objects with no atmosphere to cushion a landing. To sum it up, autonomy isn't a magic bullet, but it's a valuable tool that can help us achieve our goals in space. Each of the missions we've discussed today will push the limits of what's possible, and we'll likely see new frontiers for autonomy in the coming years. Before we wrap up, let's answer a few questions. Q. When will the first autonomous spacecraft be launched? A. In October of 2023, barring any unforeseen delays. NASA's Psyche mission will launch with an autonomous spacecraft on board. Q. How will the first autonomous spacecraft communicate with Earth? A. Psyche will communicate with Earth through NASA's Deep Space Network, the same network used to communicate with Voyager 1 and other deep space probes. Q. Can I build my own autonomous spacecraft? A. Yes, but you'll need a lot of money and expertise. NASA and other space agencies have developed open-source software and hardware that anyone can use to build their own spacecraft. But developing a spacecraft is a complex process that requires engineers, scientists, technicians, and a lot of funding. Thank you so much for watching. If you enjoyed this video, Be sure to subscribe for more deep dives. And check out the end screen for more videos like this one. Until next time, keep looking up.